Hello everybody, my name's George and I'm going to be presenting some work on segmenting the biliary tree from MRCP images. So firstly, a bit of background. So the biliary tree is a series of ducts that transports bile from the liver, which is where it gets produced, and into the small intestine, where it helps with the digestion of lipids. Now there are many conditions that alter the structure of the bile ducts, examples being autoimmune hepatitis and primary sclerosing cholangitis. Because of that, imaging plays an important role both in the diagnosis and monitoring of these conditions. One of the most common modalities for imaging the bile ducts is called magnetic resonance cholangiopancreatography, or MRCP. This uses heavily T2-weighted pulse sequences to non-invasively image the bile ducts. And just at the bottom of the screen here, I'm showing two example maximum intensity projections of MRCP images, just to give you an idea of what they tend to look like. And I've also annotated on these images where some of the major ducts are. So why might segmenting the biliary tree be clinically useful? Well, in current clinical practice, MRCP image analysis is primarily qualitative, and this can result in quite a high interoperator variability. Because of that, there's growing interest in providing more objective assessments using quantitative biomarkers. And given a segmented model of the biliary tree, we can do things like compute metrics describing the entire biliary tree, for example, the whole segmented tree volume, or we can even provide measurements of individual ducts. Now, segmenting the biliary tree from an MRCP image does have a number of challenges associated with it. One is that the duct contrast can be quite variable, with thin ducts appearing to be very faint. Another problem is that some bile ducts can have a high tortuosity, and the biliary tree itself can have a large number of bifurcations in it. Yet another problem is that MRCP images will often have a lot of high-signal gastrointestinal structures, some of which can lie very close to the bile ducts. Now, what this really means is that a direct manual segmentation from a raw MRCP image is actually quite a challenging task, even for an experienced clinician, and it becomes even more challenging when you also want to accurately preserve the duct dimensions. So to date, there hasn't been all that much algorithmic work done on segmenting biliary trees from MRCP images. However, because bile ducts are structurally quite similar to blood vessels, methods that were originally proposed for blood vessel segmentation are actually a good place to start. And at Perspectum, we've developed a software package called MRCP+. So this is currently the only FDA-cleared medical device for segmenting biliary trees from MRCP images. And the way it works is the image gets loaded into the software, at which point it'll undergo tubular enhancement and thresholding, currently using the Frangi vesselness filter. At this point, the user takes over and clicks on those collected components that they believe correspond to bile ducts. And finally, the software will take these and then produce a final model of the biliary tree. And it'll also do things like compute the duct diameters, the total tree volume, the duct center lines, and a number of other metrics too. Now, MRCP Plus has actually been shown to have quite good reproducibility and also to give reasonably good duct diameter measurements. However, we do believe there's some room for improvement, and in this talk, I'm going to be talking about a potential alternative approach to this Frangi vesselness filter. So firstly, just a bit of background on Frangi vesselness. So the way it works is that every image voxel, you compute the image Hessian using Gaussian derivatives. Now the eigenvalues of these Hessians basically give you the axes of the best fitting local ellipsoid. What Frangi vesselness will do is it takes these eigenvalues and computes a score of how likely each voxel is to contain a tube-like feature. Now for a vessel, you'd basically expect the best fitting ellipsoid to be fairly thin and stretched out in the direction of the tube. In other words, it should have high eccentricity. Now, often you have to deal with vessels of varying sizes in these images. So because of that, you tend to have to repeat the calculation of the Frangi tubeness score using a range of standard deviations, which corresponds to varying the spatial scale. To get the final score, you then take the maximum vesselness score over all the scales being considered in every voxel. Now, Frangi vesselness does suffer from a number of problems. One is that it can be very sensitive to noise in the raw images. And yet another problem is that the model assumptions being made will often break down at both bifurcations and endpoints. For example, at a bifurcation point, the Hessian eigenvalues often have quite similar magnitudes, which would actually correspond to a spherical rather than a tubular structure. So because of that, we've been investigating an alternative approach based on the local image phase. Now, local image phase has actually been successfully applied in a number of other areas of medical image processing for doing feature detection, including, in fact, in the detection of blood vessels. And some of the advantages of these approaches are that they make fewer assumptions about the underlying images, and they're less sensitive to contrast than derivative-based approaches like Frangi. So local image phase is generally calculated using bandpass filtering, which is computationally also quite efficient. So in this work, we use the Mellor-Brady bandpass filter, and this is often a popular choice in imaging applications because it has a sharp peak and a fast decay to zero, which can help reduce errors due to blurring. Here I've plotted out an example Mellor-Brady filter in 1D, which is this blue even function here. And I've also plotted out another filter, which is just a Hilbert transform of the even filter. And this Hilbert transform filter is basically just an odd filter, and it's this pair of filters that you would need to calculate the local image phase in 1D. Just to give a bit of an idea of what these filters are actually doing, here I'm showing scalograms showing both the even and odd filter responses for a simple square wave signal in 1D. And you can see that the odd filter tends to have a high response towards the edges of the signal, while the even filter will tend to have a high response towards the center of the square wave, which is a symmetric feature. So one other way of looking at this is that here I've subtracted the odd scalogram from the even scalogram. So the red bits are where the even filter dominates, which tends to be at symmetric features, while the blue bit is where the odd filter dominates, and this tends to be asymmetric features like edges. And this is true over quite a wide range of scales. We can actually combine the even and odd filter responses together to give us something called the analytic signal. So the analytic signal is a complex number whose real part is the even filter response and whose imaginary part is the odd filter response. And like any complex number, we can write this out as a complex exponential. And the argument of this complex exponential is called the local phase, and it's basically a measurement of which filter response is dominant. In other words, local image phase will basically tell you whether you're more likely to be at either a symmetric or an asymmetric feature. Now we can actually extend all this to multiple dimensions to look at images using something called the Riesz transform. And this is basically just an extension of the Hilbert transform to multiple dimensions. Beyond that, the analysis is broadly quite similar. Now here I'm showing some example filter responses both for the even and odd filter for a simple tree-like phantom. And you can see here that because ducts are symmetric features, they tend to have a higher even filter response, including at bifurcations, which are also symmetric features, while the odd filter will tend to have a higher response towards the edges of the ducts, just like it did with the 1D square wave signal. Now, because we expect ducts to be symmetric features, in other words, to have a high even filter response, and we expect this to be true over a whole range of scales, we can actually score how likely each voxel is to contain a symmetric feature using something called phase symmetry. So the way this works is at every bandpass scale, we calculate the even and odd filter responses. You then can calculate something called the local energy, which is basically like a total filter response. And at each scale, that helps you discriminate between signal and background. Finally, we calculate the phase symmetry, which is basically a weighted average of the even filter response over a whole range of scales. It also contains a noise threshold, which in this work we compute using a previously described method. And you have this epsilon parameter here, which is a small number to handle division by zero errors. So here's a clinical example showing both its Frangi vesselness map and its phase symmetry map. And you can see that phase symmetry does a better job of suppressing the background while still enhancing the ducts. However, there is actually further room for improvement with this phase symmetry approach. And it also does have this tendency to enhance some of the gastrointestinal structures too. Because of that, we actually investigated using some more regularization methods. And in particular, we wanted to try and suppress non-tubular structures. Now, interestingly, it turns out that the Riesz transforms that we use to calculate the local image phase are actually equivalent to using smooth derivatives. Now, because of that, we can actually calculate a smooth version of the image Hessian using a second-order Riesz transform and our bandpass filter. And we can take the eigenvalues of that smooth Hessian and then calculate a tubular score in exactly the same way that Frangi does. And we call that the Riesz vesselness. So one other thing with symmetry filters is that you can sometimes end up suppressing the edges of thicker ducts. However, there's another parameter called phase asymmetry, which is exactly the same as phase symmetry, but calculated using the odd filter response. And it tends to take high values towards the duct edges. And this is another thing that we calculated as well. So we then put all that together in order to define a regularized phase symmetry map. So the way that was defined in this work is that any image voxel with a low phase symmetry value and a low vesselness score got filtered out unless it was likely to lie close to a duct edge. Now you can see on this clinical example that I showed before that this regularized phase symmetry approach does a much better job of suppressing the background while still preserving most of the bile ducts. Now, it is possible that there are other, potentially more sophisticated ways of doing the regularization than simply with thresholding. However, we found that this approach already gave quite good results in our work. And the thresholds that we used here were fine-tuned using a number of clinical data sets and some phantom data as well. Now, if we're going to use a Frangi-style regularizer that contains its tubular score, we need to make sure we don't inherit Frangi's problems at bifurcations. Now, the good news is that because with our method, the thresholding only really kicks in for low phase symmetry values, you can see that for the simple tree-like phantom example, we're able to preserve the bifurcations quite effectively. Now, here's a clinical example just to show that this isn't the case in purely simple phantom examples. So this case has quite a prominent bifurcation, and you can see that Frangi once again really struggles right at the center of the bifurcation. And in fact, it tends to thin out some of these thicker ducts as well. On the other hand, our regularized phase symmetry approach is able to preserve the bifurcation while also keeping the diameters of the ducts much more similar. Now, many diseases of the bile ducts can affect their dimensions, and so we need to make sure that we can accurately measure the dimensions of the bile ducts using our proposed method. So to test this, we used a 3D printed phantom with known duct diameters, and we filled the ducts of this phantom with a solution that has similar T1 and T2 values to bile. We then scanned the phantom on a Siemens Prisma scanner using a turbospin echo MRCP sequence. We then took the images of this phantom and we computed the regularized phase symmetry maps and the Frangi vesselness maps. We then loaded these into the MRCP class software in order to measure the duct diameters. Now, because Frangi vesselness does have this tendency to thin out thicker ducts, MRCP Plus already has a way of handling this. And what it does is it takes a thresholded Frangi vesselness volume and a thresholded raw image, which tends to contain most of the thicker ducts, and it takes the union of those two thresholded images and then calculates the diameters of that unionized image. And to keep it a fairer comparison, we've included that in here as well. Having modeled the ducts, we then co-registered them with a ground truth phantom, which is reconstructed from the phantom specification files. Then at every point, we measured the difference between the true and the measured duct diameters. Now here, I'm showing some results from a Bland-Altman style analysis. So the bias is the mean difference between the true and measured duct diameters, and the limits of agreement are the bias plus or minus 1.96 standard deviations. And you can see that with our proposed approach, we got the lowest overall bias, while using Frangi vesselness on its own actually gave the worst overall results. Now, it is true that you actually get tighter limits of agreement using the default MRCP class method. However, if you look more closely, you will see that our proposed method still gives you limits of agreement that are comparable to the image voxel dimensions, and that's still a very encouraging result. And what it's really telling us is that with our proposed method, we can get good background suppression, better performance of bifurcations, and still get reasonably good diameter measurements. So one point I'm going to touch on extremely briefly is that some MRCP images are really challenging because they have worse duct contrast than normal. Now, it's often claimed in the literature that phase-based approaches are less sensitive to contrast than derivative-based approaches like Frangi. And while we haven't explored that at length here, some very preliminary results do suggest that that's the case for us as well. So just to conclude, we've proposed a new method for bile duct segmentation based on phase symmetry, and we've compared it to an existing approach that's using Frangi vesselness. Now, our proposed approach gives good background suppression, and it also performs well at duct bifurcations, while still giving reasonably good duct diameter measurements. And one other interesting point is that our method might also perform quite well on challenging low contrast data, and that's something that we aim to study further. So thank you everyone for listening, and if you have any questions, please feel free to get in contact with me.